Hello, this is Dr. Baxley. Welcome to the lecture video for Chapter 6, Thermochemistry. This is Part 3, Calorimetry. In this video, you'll learn about measuring heat energy changes for simple systems, not chemical reactions yet. I hope you have your printable lecture notes and your calculator. There will be lots of calculations in this particular video. The specific heat capacity is a property of matter that determines how much energy needs to be applied to change the temperature of that particular substance. Specific heat capacity values are listed as units in joules per gram degree Celsius or joules per gram Kelvin. Regardless of the units used, the value of specific heat capacity always has the same numerical value. So water would have a specific heat capacity of 4.184 joules per gram degree Celsius or 4.184 joules per gram Kelvin. The specific heat capacity depends on the substance, and it shows how much energy is required to raise 1 gram of material by 1 degree Celsius. Here are two examples. The specific heat capacity of iron and aluminum are listed there. We could ask which absorbs more energy to raise the temperature by 1 degree Celsius, iron or aluminum. By looking at the specific heat capacity values, we can see that aluminum has a higher number. It takes more joules of energy to raise 1 gram of the material by 1 degree Celsius than iron. Which material would get hotter if 100 joules of energy were applied to 1 gram of the material, iron or aluminum? Well, it takes more energy to raise the temperature of a piece of aluminum, so that same amount of energy would change the same mass of iron by a larger temperature change. Here's a sample problem that relates to specific heat capacity. Before solving a specific heat capacity problem, it's important to recall the relationship between the heat energy change of a substance Q and the mass of the substance, specific heat capacity of the substance, and the delta T of the substance. It's also helpful sometimes to draw pictures of what might be happening in a particular scenario. For example, in this question, question A, a piece of copper is being heated up. It's then being put into some water in part B. We can visualize that with this little diagram. Here's a piece of copper, it's getting heated up, and then it's put into some cooler water. Because the copper energy is hot, it has more thermal energy, and some of that energy will be released to the water. It's important to note that in these kinds of problems, we're always going to assume that no heat is lost to the surroundings or to the container. What that means is that any heat energy change for the metal is going to be equal to the heat energy change for the water. However, there is a little negative sign here because the heat energies are going in different ways. The copper is releasing energy, the water is absorbing energy. We can work the problem for the copper by taking the heat energy for the copper and setting it equal to the mass of the copper times the delta T for the copper times the specific heat capacity for the copper. The mass of the copper is known. We can calculate the delta T for the copper. It's important to note that delta T is always calculated to be TF minus TI, or final temperature minus initial temperature. In this case, the initial temperature of the copper was the 25 and the final was the 312. And multiplied by the specific heat capacity. This all works out to be 1.39 times 10 to the 4th joules of energy. Now question B asks about the amount of energy that was used to heat the copper and how much water could be heated up by that amount. We can calculate Q of water. We know that's equal to the amount of energy the copper absorbed. That's going to be equal to the mass of the water, which we don't know, times the delta T of the water. Since we're heating the water again in this case, we'll assume that's 50 minus 25 degrees Celsius, times the specific heat capacity of the water. And that's something you should know. 4.184 joules per gram degree Celsius. We can solve for the mass of the water by dividing the energy by the change in temperature and the specific heat capacity of the water. And that works out to be 133 grams of H2O. Here's the next problem, solving for the specific heat capacity of a metal that's being placed into a liquid. In this case, the liquid's no longer water. It's a liquid called ethylene glycol. So pause the video, see if you can work this problem by yourself. Okay, here's the solution. We can calculate the Q of the ethylene glycol because we know its mass, 100 grams, times the delta T. In this case, it's 2.4 degrees Celsius. And we know its specific heat capacity value. That works out to be 580.8 joules. We know that the Q value for the ethylene glycol is going to be equal to the negative Q value for the solid that's being placed into it. One substance is gaining energy, one substance is releasing energy. Since the ethylene glycol energy was positive, we know that the Q value for the solid is going to be negative. We know that negative 580.8 joules of energy is going to be equal to the mass of the solid that's being added times the delta T remember delta T is T final minus T initial. So in this case, that would be the initial temperature of 53.0 degrees subtracted from the final temperature of 14.4 degrees, because that was the temperature that the solid eventually rose to or fell to once it cooled off as it warmed up some of the ethylene glycol. And we don't know the specific heat capacity of the substance, but we can calculate it. The CS is going to equal the negative 580.8 joules divided by the mass divided by the delta T, and the specific heat capacity therefore is a positive number and is equal to 0.153 joules per gram degree Celsius if we follow the units. Keep in mind that the delta T value is going to determine the sign of Q, because mass is always positive, CS is always positive, so delta T is what relates to Q in terms of being positive or negative. That's the end of this section of the video. We'll learn how to do calorimetry calculations for chemical reactions in the next video.